Welcome to lecture 23. In lecture 23, we're doing chapter 8 in your Wade book. And the title of chapter 8 is Electrophilic Addition to Alkenes. So the last chapter we talked about how to synthesize alkenes, and we talked about the stability of alkenes. So we make alkenes by either an E1 or an E2 mechanism. And we talked about Zatsev's rule, and the opposite of Zatsev's is Hoffman. And if you remember, we decide based on these mechanisms the reactivity profile is still tertiary is greater than secondary primary for both E1 and E2, but it is the strength of the base that determines whether you have E1 or E2. So E1 uses a weak base. When we think of weak bases, we think of like methanol or ethanol or water. These are proteinizing solvents as well because they're polar protic, so they can stabilize a carbocation. So you're still looking at the carbocation. You have to have the most stable carbocation for the E1. And then we talked about the rate is proportional to that substrate, so to your electrophile. Now, the base for E2 has to be strong. So we think of a negative charge like sodium hydroxide. We think of like sodium methoxide, potassium terbutoxide. So these are all have negative charges, and these usually need to have some kind of polar aprotic solvent. We talked about like DMF and acetone, and these do not have a proton that can solubilize or stabilize that negative charge. We talked about the Hoffman bases. You have triethylamine. These are big bulky bases. We've talked about diisopropylamine. So diisopropylamine looks like this. Okay. So there's a couple more other bases, and they will give you the less substituted product, alkene. So if you have a di versus a tri, it's going to give you the di versus the tri. Zatsev's is going to give you the more substituted alkene. And we've learned that the more substituted alkene is more thermodynamically stable than the less substituted. Okay, so that's about how to synthesize alkenes. Now chapter 8 is going to talk about the reactions of alkenes. And you're going to have a lot of reactions of alkenes in this chapter, folks. We're going to have Pogel exercises 11A, 11B, and 11C. And I want you to get out your reaction sheets, and I'm going to show you how to fill those out. And I think you need to have one reaction sheet per reaction. And we're going to start off with this. I'm going to give you an overview of what an electrophilic addition looks like, and then I'm going to list the different reactions, and I'm going to show you how to fill out the reaction sheets, and then we're going to go into your Pogel exercises. Okay, so for your reaction sheets, you have, and they're on Blackboard, you have your starting substrate, and that's a functional group. So this is all going to be alkene, so you can write the alkene. I like to put in the actual word, but then also it's good to put an example, okay? So this would be CH3, CH2, CH, CH, CH3, CH2, CH3. Okay, so that would be the condensed formula. reactants, and solvents, conditions. Okay, so the different reactions are going to be different. The first one we're going to talk about is we're going to add, let's say, HBr. Okay, so we're going to add HBr, and a lot of times the solvent is usually like ether. So what's an ether? Like this is diethyl ether. It looks like a little bat right there. Diethyl ether, tetrahydrofuran. So if you see THF, and the more problems you work in the book, you see those solvents. So you have to work problems, folks. Okay, the product here, which is your functional group. And I'm not going to fill out these every time for you. I expect you to do it for yourself because you're also going to need those in organic too. So your product, your functional group here, you're going to see that it's going to be an alkyl halide. So that's the name. And what you're going to see for your product is you're going to get, let's make this green here, HBr. So you're going to find that H adds here. Put a hydrogen there. And you're going to see that Br will add there. Okay. So, and you can even give this a name. 1, 2, 3, 1, 2, 3, 1, 2, 3, 4, 5, 6. So you should know that this is 2-bromo, 2-methyl hexane. Okay, so just try to describe those. It's a good exercise. And then here, stereochemistry, regiochemistry, chemistry, or intermediates. So like if you have a carbocation, an intermediate would be your more stable carbocation for like E1 and SN1. Stereochemistry for your E2 is anti-180 degree paraplanar. Stereochemistry for SN2 would be backside attack, so inversion of stereochemistry. This has regiochemistry, okay? So this one has regiochemistry, and it also has an intermediate. And so that intermediate is going to be, you're going to see that the first thing that happens is the H adds, okay? And then you're going to get a carbocation, okay? So that's why this is a tertiary carbocation here. And then this also gives a regiochemistry, because regiochemistry is when you have a hydrogen is going to add to one carbon, and then the bromine is going to add to a different carbon. Okay, so you have two different carbons to choose from here. You have this one or this one, and you see that the hydrogen adds to the less substituted carbon, and then the bromine is adding to the more substituted carbon. And the reason why is because of this intermediate here, you have to get the more stable carbocation. Okay, so that's how you fill out that, and then you'll notice that there's a whole box that says draw reaction mechanism below. Okay, so that's kind of when you're doing your POGL, I want you to fill out these reaction sheets. So if you need to print them off for yourself, that would be good. So let's look at this reaction. And so the title of this can be the addition of HX to alkenes. And the mechanism is electrophilic addition to alkenes. Okay, so, excuse me, alkenes are nucleophiles. So, do you remember how I make my nucleophile like that? And I always do this double bonded underline. And it's because alkenes are nucleophiles. And so they use these pi electrons. They got 2 pi electrons that can go and attack an electrophile. So what does that look like here? Well, let's do this reaction above. Okay, so if we have this reaction, and we are going to add, we'll do HBr. Okay, so if we're going to add HBr there, then you always draw the nucleophile to the electrophile. Okay, we always do that. So your electrophile here is this hydrogen. Okay, you know HBr, you've seen that in your acid-base reactions. So you draw from the pi bond to the H, and then those electrons that are bonded with the HBr go to Br. And then you have to draw your intermediate. And so the H is going to go to the less substituted carbon. So we have either this carbon here that has one carbon coming off of it, or we have this carbon here that has two carbons. So it's going to go to the less substituted so we can get our more stable carbocation. And this you can see is a tertiary carbocation. And these are the mechanisms that we're going to learn in our POGIL exercises. This is just kind of an overview. All right, now we have Br minus. And so now, this was step one. And so that's electrophilic addition. You see how the electrophile, which is H, plus added to the nucleophile, which was your alkene. Your alkene is the nucleophile. And we get, step one, we get a carbocation. And we have to form the most stable carbocation. And we're going to talk about this as a new rule. We're going to give it a name. It's called Markovnikov's rule. Markovnikov's rule. Okay, that's Mark's rule. And we're going to talk about what Mark's rule says, but basically it makes them most stable. You want to always get the most stable carbocation. And that's what you're going to see over and over. There's two steps in these electrophilic additions to the alkenes. Okay, now the bromine comes in with its electrons, and now this is your nucleophile, and that's your electrophile. And you only need one single arrow there, and then you draw your product. So you added the hydrogen to the carbon-carbon double bond, and you added the bromine. And you made an alkyl halide. Okay? Now, you know when you have the carbocation that this is an sp2. It has a unhybridized p orbital above and below, in which the electrons from bromine donate to make that bond. So the bromine can add from the top or the bottom. Okay, so there's no stereochemistry here. It's just, but you do have regiochemistry because you're choosing to make the more stable carbocation, which is Markovnikov's rule. Okay, now I'm going to go to your book and I'm going to specifically write Markovnikov's rule. And that is on page 400. So Markovnikov's rule states that the addition of a proton acid to the double bond of an alkene results in a product with the acid proton bonded to the carbon atom that already holds the greater number of hydrogen atoms. So an electrophilic addition of, so in electrophilic, we call it E's. No, that's a different one. Electrophilic addition of alkenes, electrophilic addition of alkenes, Mark's rule, you do Markovnikov, an electrophilic addition to an alkene, the electrophile adds in such a way to generate the most stable intermediate. So whenever you add, and sometimes that's going to be a delta positive, partial positive, and sometimes it's going to be a full carbocation. And that is Markovnikov's product. Some reactions are going to be anti-Markovnikov. And so I'm going to give you an example of HBr that's anti-Markovnikov. Okay, so let's do the same starting material that we did before. Okay, and so what happened, there were a few scientists in the 1930s that were studying some reactions, and they opened up an old bottle of HBr. Okay, so they opened up an old bottle of HBr. Well, this is the product that they got, and it surprised them. Okay, so they got Br here and H here. Okay, so they didn't understand this, and because this is the anti-Markovnikov regiochemistry. Okay, so this is opposite what we saw. So here we have the Br going to this less substituted carbon, and we have the hydrogen going to the more substituted. This is anti-Markovnikov regiochemistry. So what happened was, it's a different mechanism because this old bottle of HBr generated peroxides. And now you can actually add like hydrogen peroxide, or you'll see just peroxides. Okay, so a peroxide is an oxygen-oxygen bond, and it does a homolytic cleavage because this is a very weak bond. Okay, and so you end up getting CH3O radical. A lot of times you will need to add some form of heat, or you might see light, okay, to generate this free radical. So this is not an electrophilic addition mechanism. Okay, this is not. This is a free radical bromination. Bromination of alkenes, and you're responsible for this, okay? So this is a free radical bromination of alkenes, and the first thing to do, you have to have an initiation step anytime you do free radical mechanism. So you have some kind of ROOR, okay? R can be any kind of carbon, and you show your homolytic cleavage. You do this with your fishhook arrows, and then you have propagation 1. In propagation 1, you have your alkene, and you have your new radical. We'll just call it CH3O radical. Now what happens is the free radical can add no, we're not done. We have 2 initiation steps. Okay, so this generates, this is a small amount. So that's initiation step 1. We're going to have initiation step 2. Now this free radical will react with HBr and generate the bromine radical. So this will come here, and it'll take the ROH plus the bromine radical. Okay, so now we have the bromine radical in our propagation 1 step, and the bromine radical is the first thing that adds. Okay, so then this goes here and this goes here. See, we have three of those, three arrows. And then we redraw this. And so this is different because the bromine adds here to generate a free radical. And the free radical, this is still the more stable free radical. We need to have the radical on the more substituted carbon. And in your propagation step 2, it is this free radical now that will propagate and make another radical. So we'll add this with another HBr, and then this comes, we have 3 fishhook arrows, and we form put the H there, the H adds there, and generates another bromine radical. So there's your propagation step 1 and 2. Could you do bond dissociation energies on this? Yes, because these are homolytic cleavages, and you could determine that this is exothermic. But I want you to understand that this is a different mechanism. It's free radical mechanism, and it's but it's given you the Markovnikov product with alkenes. So now you know 2 ways to make alkyl halides from alkenes. So you know how to go from an alkene to an alkyl halide using HBr. But one of them, HBr, will give you Markovnikov's product. And if you do HBr with peracid, you get the anti-mark. All right, so before we get into our POGO exercises, now that you understand what electrophilic addition is, and you understand Markovnikov versus anti-Markovnikov, I want you to look at table 8.1. Okay, this is on page 398. I'm sure you have that table in your PowerPoints on Blackboard. Do you see all those reactions? Okay, each one of those reactions needs a reaction sheet. You have to be able to predict the products, starting materials, and reagents on your assessments. And we're going to work through POGLs 11A, 11B, and 11C. And I'm here to tell you 11A, the reagents that you're adding is HCl, or it could be HBr, or it could be HI. We don't do HF, okay? So that's, you're going to see that as HX. So these are the electrophiles we're adding. What's the nucleophile? What's the nucleophile? It's the alkene. Okay, so the nucleophile is the alkene. Most reactions, they always have a nucleophile and electrophile. So there's your nucleophile, and this is the electrophile we're adding, because this is electrophilic addition to alkenes. Okay, so what electrophile are we adding? We're going to add HCl, and we just did that reaction. And it's going to demonstrate Markovnikov versus anti-Markovnikov. And then, like I said, what's not on 11A is the free radical, but we went over that reaction. Okay, 11B is going to talk about adding oxygen, the addition of oxygen. And you're going to do 3 ways to make alcohols. Okay, you're going to make alcohol. So you're going to go from an alkene to an alcohol. Now on the 11A, we went from an alkene to an alkyl halide. Here we're going to make alcohols, and there's 3 ways. And one of this is going to be acid catalyzed hydration. So your reagents are usually going to be sulfuric acid and water. Okay, that's one way. We've got three ways. The second way is called Oxymercuration of Alkenes. So we're going to use mercury acetate in water. We're also going to show you that if you change the water to alcohol, you can make ethers. So that's going to be another reaction that you'll need to get in your protocol. The second reagent you have to add will be sodium borohydride. You have to put a 1 and a 2. It will be important. And the third way to you're going to find that these are both Markovnikov. Okay. And then the third way is going to be hydroboration. See if it's on there. Hydroboration. And that's BH3. And then the second thing will be hydrogen peroxide and sodium hydroxide. And that's going to make an anti-mark. And it's important to be able to control the regiochemistry. That's why we have to have options. So we're going to learn when you would use 1, 2, and 3. If you want the Markovnikov product, you would use 1 and 2. And we're going to talk about how 1 makes me sad because you get carbocation rearrangement. So I would never want to do that reaction unless I wanted carbocation rearrangement. Oxymercuration would be the choice there. Notice on your table 8.1, this is called hydration. So even though you have 9 reactions in that chart, 3 of these are under 1. Okay, so that's 9, 10, 11, 12. So that already gives you 12 reactions. The halogenation reaction, this is called halogenation reaction on that chart, but I've showed you 2 reactions on halogenation reactions that you're responsible for. Okay, I'm just giving you an overview. 11C is electrophilic additions. We're going to look at the cyclic intermediates. Okay, so we're going to look at cyclic intermediates, and the reactions we're going to add Br. We're going to add halogens. So this is halogenation. So that's up there on the chart. We're also going to add water in the halogen, and that's called halohydrin formation. Each one of these should have their own chart. Okay, so I look at that. Halohydrin. We're just going to do epoxidation of alkenes, and those are going to be, my favorite is MCPBA, and that is metachloroperbenzoic acid, but you'll find that you can use any of these per acids. See, there's two oxygens bonded, and this is going to deliver an oxygen to make an epoxide. What does an epoxide look like? An epoxide is a 3-membered ring, so that would be an epoxide. So that's an epoxidation. And we're also going to open epoxides. So then we will open epoxides. You will do that under acid, and they're going to give you different regiochemistry. And then we're going to do base opening epoxides. So that's model 3. And then that is 3 reactions. We're going to get another one in there, number 4. And number 4 is we're going to do syn dihydroxylation reactions. And you're going to see that the reagents for that is potassium tetroxide, permanganate, potassium permanganate, or you can use osmium tetroxide. It's a little bit more expensive, but they're going to give you a diol. That means across that carbon-carbon double bond, you get the diol. You're also going to know this has stereochemistry, so we're going to have dashes and wedges there, okay, because it's actually called syn dihydroxylation. You're going to learn that syn means it's delivered on the same side, and then you're going to learn about ozonolysis. Ozonolysis, and that's where ozone, O3, cleaves the carbon-carbon double bond to make aldehydes. And that is oxidative cleavage. And those will be your reactions. We're also, when I look at this, that's called epoxidation. You have oxidation to cleavage, dihydroxylation. The other reactions that we need to include, and I will include that right here so then we can just go straight into our POGL. So the other reactions that are not included in your POGL, but they're included in Table 1, is called hydrogenation of alkenes, and the other one is cyclopropanation. I will talk about cyclopropanation reaction. I'll add that onto your POGL 11C because that's a cyclic intermediate, and so we'll keep with that. But I want to do hydrogenation of alkenes. That mechanism is different than your electrophilic addition, really, and that is on page 425 in your textbook, and it's called Catalytic Hydrogenation. Of alkenes, and I'd like for you to do a reaction sheet on that. So if we did our typical reaction here, the reagents you would use is you have to use hydrogen gas, and then you would use a catalyst. Okay, and your catalyst can be palladium, platinum, or nickel. So any of these three metals. And what happens is this metal gets saturated with hydrogen gas in it. So when you put your little metal in there, kind of looks like lead or something, it adds to the metal. So this is your metal. It stirs in your reaction. And then what happens is this alkene is attracted. These electrons that are above and below this molecule will sit on top of this, okay? And then the hydrogen will add. Okay, so the hydrogen, so this adds and this adds, and it's concerted. And we know what concerted means. Concerted. It's happening at the same time. So we're going to get stereochemistry. Anytime we have concerted, it's in concert, bonds are being made and broken at the same time. That's stereochemistry, and this is syn. Okay, so that means you have to add this with either both wedges or both dashes. Either way is correct. But the hydrogen will add, should make it red, will add to both of these. Keep in mind you already have a hydrogen on there. So that's syn hydrogenation, hydrogen hydrogenation. And you can see how that is a different mechanism because it's, and once this alkene, so your alkene is becoming an alkane, see the different functional groups? It is no longer attracted to the metal. And think about a metal. A metal is very electropositive. So these platinum, nickel, and palladium are very positive. They have these empty d orbitals. Okay, they need electrons. They have lots of orbitals, and they need electrons. So they're very attracted to this pi bond. It's like a very electrostatic kind of attraction. And then so the hydrogen that is just immersed in this metal here will then go and make an alkane. And then you can isolate your alkane. Let's see. let's stop here and then I'll make different slides for presentations for each 11A, B, and C.